This conference will now be recorded.
Good morning, friends. We will wait for a few minutes. Let them to join here. Okay, right. Let them to join here. Up to last class, we discussed about inductance of a single phase line, right? So let me. I will recall that what are the what we are discussing in up to last class. The derivation part that is for inductance value. So inductance due to internal flux, inductance due to external flux, and then inductance of a single phase line, single phase two-wire line, and then inductance of a composite lines. So these are the topics we discussed, and this derivations is belongs to the single phase circuit. Single phase in the sense it has only two conductors. One is phase and another one is neutral. Right? What is the inductance? Where inductance for due to the internal flux? What is the inductance due to internal flux? Anybody? What is the internal flux? Sorry, inductance of due to internal flux. That is 10 power minus 7 by 2, right? Next, inductance due to the external flux is 2 into 10 power minus 7 ln d2 by d1. So these are the inductance we derive based on that single phase circuit. Now onwards, we are going to derive the inductance value three phase circuit. And one more thing, in most probably in a transmission system, the three-phase line consists of a double circuit. Do you know that what is the advantage of double circuit? What is the advantage of double circuit? It consists of a three-phase line. See here, I'm showing now. See, this is the three-phase transmission line. It has the two layers, right? So what is the main advantage of it consists of a two layers means suppose it is R Y B and it is also R by B. Now what is the use of these two double circuits? At what purposes we are using? Because the main thing is reliability. So why it is called as reliability means suppose it has the two couples, right? If there is an event of fault and repair, one of the lines should be disconnected. At that time, if there is not the interruption is not occur in this type of couple double circuits. Why? Because suppose it is a circuit 1 and circuit 2. If any fault is occur or any repair is going on here, we can get the supply from this one phase, one circuit. So that is the use of double circuit three phase we are using in the transmission lines. Now, so this is the circuit 1 and it is the circuit 2. Now we are going to find that what is the flux linkage between these two parallel conductors. So here R by B and this one R by B, these two are in parallel conductors. And now we are going to derive that what is the flux linkages between among these two circuits, right? So generally, how these phases are connected in a three-phase system is suppose if it is R, if it is Y, if it is B means here they won't connect like this R by B, so they will connect like this R Y B. So what is the use of this type of arrangement means suppose if you connecting like this, the GMD will be the GMR will be increases, right? Do you know that the inductance is equals to 2 into 10 power minus 7 ln GMD, this is dm divided by ds, right? While observing this equation, that is inductance, that is L value is inversely proportional to ds, that is self GMD, that is self GMD. So it is also called as GMR, geometric mean radius. Now, when the geometric mean radius is reduced, the inductance value will be, so it means that inductance value will increase. Now, when the GMR will be increased, the inductance value will be reduced. Now, if the connecting like this type of arrangement R by P and from downwards R by P, now the distance between these two conductors will be increases. Now, when the DS will be increased, there is a inductance will be reduced. So when the inductance will be reduced, there is no the power losses will be occur in the transmission line is comparatively reduced because of this type of arrangement, right? So that is the main. So this is why in three-phase transmission lines they are connecting R by P phases in this manner. So one circuit they are connecting that R by P from upward to downward. In another circuit they are connecting from downward to upward. Due to why? Because this is for only reduce the losses. So how we can reduce the losses means by reducing the inductance, by increasing that GMR value. So the distance between R and R will be increased, right? So if the distance will be increases, the inductance, the flux linkage will be reduced automatically. Inductance also reduced. Due to this reason, the power losses will be comparatively reduced in the three-phase transmission lines. So this is why generally in three-phase transmission lines we are using the double circuit. So first one is for reliability, for continuous supply without any interruption, for maintenance purposes. So suppose if it is any circuit is required maintenance or repair or replacement, we can go for another circuit for continuous supply. So there is the use of double circuit we are using in the three-phase line. Now in this class we are going to derive that three concepts. What are the three concepts means? The first one is the flux linkages of a parallel current carrying conductor, and next one is inductance of three-phase lines with symmetrical spacing and unsymmetrical spacing. So these are the three topics we are going to discuss in this class. See, in the first unit we have the two derivations. One is belongs to the inductor, another one is belongs to the capacitor. In your external exam, definitely you will get one most important question from inductance derivation as well as capacitor derivation. So if you are well aware about inductance derivations, it is comparatively most similar to the capacitor derivation. So how we can remember this? How we can know this? By practicing. So if you practice more and more, then only you can remember them. What are the derivations? What are the internal steps? What are the final equation for the particular case? So you can remember that. So it is only possible by the practice and number of practice times. Then only you can attempt that question. Now we'll go for today's class. So today's topic is inductance of a three-phase circuit. So now onwards we are going to derive the inductance of a three-phase line. Right. So this is our topic we are going to derive in today's class. So just remember that what we discussed in the previous classes. If you know that equations and derivations, then only you can understand this derivation. That is three-phase circuit. It is nothing simply. So in that first single-phase circuit, we are deriving the two conductors. At the same time, in three-phase circuit, we are deriving the for three conductors, right? So most probably both are same, but here some modification will be there. So you have to understand that. So while discussing, if you have any doubts, just clarify within the class. Then only you can understand the derivation. The first one is the flux linkages of a parallel current carrying conductors. Just now I told you that in a three-phase circuits we have the double circuit in three-phase transmission lines. So this is the circuit one. It consists of R, Y, P. This is circuit two. It consists of R, Y, P. Just keep remember that this is the most important general question in transmission system. how the double circuit, how the phases are connecting in the double circuit RYB. So in circuit one circuit one, the phases are connected from upward, that is RYB. In second circuit, they are connecting R by B. Why? Because we have to increase the more distance among the same conductors. Suppose it is R dash. So the distance will be more. So when the distance will be more, then GMR will be increases, due to that inductance will be reduced. So that is the reason in three-phase circuits they are connecting like that. Now, if we consider these two parallel conductors, that is the circuit 1, circuit 2, what will be the flux linkage with respect to the conductor, one conductor? So let me derive this. Now I am considering only circuit 1. So consider a group of parallel conductors A, B, C. So here A, B, C is nothing but a R by B, R phase, Y phase, B phase. Now each of the conductors carries the current IA, IB, IC. So both all phases are having that individual currents, right? IA, IB, IC. Now I am going to find that what is the flux linkage of A. So in this A, B, C, they are flowing that I1, IA, IB, IC. But here, due to the IM, the conductor A will be generate the flux, right? And due to that flux will be flow like this. And similarly, due to the current IB, the conductor B of generate the fluxes. Due to the current IC, conductor C flux the ICs. And these fluxes, how the links with flux generated by the A. So that's why we are going to derive here. Now see here, there will be a flux linkages with conductor A due to its own current, and also there will be a flux linkages with the conductors due to mutual inductance effect. Now the flux generated by the conductor A alone is called as self-inductance, and this flux should be contact with flux generated by the B conductor as well as flux generated by the C conductor. If they are mutually interaction with these fluxes, how the total flux linkage will be happening at a conductor A. So that's what we are going to derive here. Now, if you observe this circuit, I am placing the different distance among the conductors. Now, the distance between A and B is denoted by D1, A and C D2, D3, D4. So I am placing that 5 distances, right? Now, from this, by using distances, we have to derive that what is the flux linkage with respect to the A, conductor A, right? So this is the flux linkage conductor A alone. Why? Because we have calculated the conductor A, right? When the current is flowing, that the conductor A having both internal flux as well as external flux. So what we are going to derive, what for the conductor we are going to derive, we have to consider that both internal and external flux for the particular conductor. And remaining we can consider only external flux. Why? Because this flux by A, it only interacts with the external fluxes of B and C only, right? So there is no need about internal flux of B, internal flux of C. So here we are going to find that flux of A. So for that only we have to include that both internal and external fluxes. Then only after that we have to derive that external flux of B and external flux of C. Now this is the derivation what we derived in the total flux linkage with respect due to the internal and external flux is given by equation 1. So if you see that the equation what we discussed in the first class, that is inductance due to internal and external. So this is the combination of both internal and external. If you substitute here, after simplification of this, so that is pi 1a divided by a. So that is L1a, inductance of a conductor. And instead of pi naught, mu naught, you can substitute 4 into 10 power minus 7 by 2 pi, and 2 pi 1 jar 2 the. So if you simplify this equation, and you can obtain what we obtained in the derivation. And this is the flux linkage with the conductor A due to the current P. So it means that after flux generated by the B, that flux will linkages with the flux of A, and it is given by pi 1b. And this equation we can obtain only for external flux. Why? Because when the B is generating a flux, the external flux only links with A, right? So that is the case here. And here the flux will be travels from D1 to infinity. So why? Because from A to B, what is the distance? D1, right? From here to here D1. After that, it will goes to the infinity. So we don't know what is the final distance. So from A to B it is traveling. So that the initial distance is T1. After that, when it reaches to B and the flux linkage is goes to the some point. So we don't know that. Let's consider it is infinity. So this is the flux linkage of conductor B with respect to the conductor A. Similarly, flux linkage of conductor A due to the current IC. So same thing. What we derived here, pi 1 C is equals to mu naught IC by 2 pi. Now, if you want to find the total flux linkage of conductor A, what we have to do? We have to add that all pi 1A plus pi 1B plus pi 1C. So if you add these three, then you can calculate that the total flux linkage happen in the conductor A. Let me see what will happen when we add this three equations. So this is the three equations. So the first equation is obtained from the conductor A, and conductor A having it is experienced by both internal and external flux. And second equation is we obtained from the conductor B due to the flux linkage with conductor A, and third equation we obtained from the conductor C due to the flux linkage with conductor A. So after this, we have to, for finding the total flux linkage, we have to add these three. So let me see what is the total equation. So this is the final equation, total flux linkage with the conductor A. So that is mu naught Ia divided by. So this is the flux linkage due to the conductor A, flux linkage due to the conductor B and conductor C. If we add these three, then we can get the total flux linkages with the conductor A. After simplification of all derivations, you will get the final value, right? Suppose if every term having that mu naught by 2 pi is a common, right? So take the common here, and Ia 1 by 4. So if you integrating this one, what you will get? So integration of 1 by x, you can write ln x, right? Similarly, this one ln x, like that. After instead of x, you can substitute ln r dash, ln d1, ln d2. So similarly, you can, after simplification of, you can. So what I am saying is, if you are already we discussed about single phase conductors, right? Single phase line. If you want to find the single phase line, we will get only one term. But here we are finding that three phase. So that's why we have to we will get that three terms. So that is the difference between single phase lines and three phase lines. Now we'll see that what is the inductance of a three phase lines. Suppose I already told you that in one circuit we have the three conductors, another circuit we have the three conductors. Now we are going to derive that, considering only one circuit. In that one circuit, RYB. So RYB consists of a RYB, right? So how the RYB are connected? It means with equal distance or some different distance. If it is placed in equal distance, that is called as symmetrical spacing. That suppose how we can call a symmetrical spacing is the distance between R and Y is D. Similarly, the distance between Y and B is D. So it means that how we can obtain this symmetrical spacing is when the three conductors are, that is R, Y, B, which are connected in the equilateral triangle, then only it is called as symmetrical spacing, right? So in this three phase, the most important two derivations, one is symmetrical spacing, unsymmetrical spacing. So now we are considering that first case, that is the only circuit one. In this circuit one, R, Y, B are placing in the equilateral triangle, and this type of connection is called as symmetrical spacing, right? Now, so this is conductor A, conductor B, and conductor. So I am considering the three conductors, namely A, B, C, and the distance between among the all conductors is equal. That is denoted by capital D. So that's why it is called as a symmetrical spacing between among these three conductors, and each one having that radius is R. So this is initial assumptions. So just to remember that circuit. So if you see this circuit, then you can say that whether it is symmetrically or unsymmetrically. Suppose if it is unsymmetrical circuit, means the circuit should be like this. So it is not equilateral triangle. It is just triangle, right? So that is you have to find out that what is the difference between symmetrical spacing and unsymmetrical spacing. Now this is the initial assumptions. We are considering that three conductors, namely A, B, C, and these three are separating with equal distance, capital D, and each conductor having the rate is small r. Now we will see that what is the inductance of a conductor A with respect to B and C. So we are considering only A. So if you calculating it, so the same thing will be LB and LC. Why? Because all are equal, all are in the having the same current flowing in them. So you will get same value. Now we'll see that what is the inductance of a conductor A. Now, if you want to find that inductance, so you know the relation, right? Inductance of LA is equals to pi A divided by IA. So we are calculating only for conductor A, right? So that's why we have to find the parameters all in terms of AA. Now, the current carrying by the conductors A and B and C are IA, IB, IC respectively. So these are in balanced condition. So when the all currents are balanced condition, this is the condition IA plus IB plus IC equals to 0. So that is the reason. That's why we are called as a balanced condition. Now this is the equation of flux linkage of conductor A are given by. Now let me see how it will come, right? So this is the conductor A, B, and C. So so flux linkage pi A is equals to 2 into 10 power minus 7. IA ln of the self distance 1 by r dash plus IB ln into what is the distance between A and B, D, right? So 1 by D plus 1 by C IC ln what is the distance between A and C, D. So this is the equation we obtained. So 2 into 10 power. So it has the 3 terms. 1, 2, 3. So starting we found that the inductance of a single phase circuit. So we are considering this phase and neutral. So in phase we obtain the equation L is equals to 2 into 10 power minus 7 ln by 1 by r, right? It's the same thing here. So we are considering here 3 conductors 1, 2, 3. So from A, so this is AA. That is distance between self distance. It is called as self distance, and the second term is obtained the distance between conductor A to B. So 1 by D plus IC ln 1 by D. So this is the equation. Now you have one doubt. So how we can obtain 1D like that means, suppose here the denominator is GMR, right? Geometric mean radius. So we have the 3 conductors. Just eliminate one conductor. We have 2. So square root of D into D. So square root is nothing but this one, right? D square. So square get cancelled, then you will get D. So this is the GMR, self distance. Next, after that, if you find this equation, that is phi A. So we have the condition, that is when the all currents are in balanced condition. So IA plus IB plus IC. So what is the importance of this equation means, suppose if you want to find the LN, we have to equating this equation by psi A by IA. But we have IB and IC, right? So we have eliminate these 2 currents, IB and IC, we have to eliminate them. How we can eliminate? By using this equation. That is balanced condition, all sum of the current is equals to 0. Now from this equation we can write IA equals to minus of IB plus IC, or IB plus IC is equals to minus IA. If you observe these 2 terms, it has the both common terms is ln 1 by D. So if we take ln 1 by D is common, ln 1 by D into IB plus IC. Instead of IB plus IC, we can substitute minus IA. So finally we will get psi A is equals to 2 into 10 power minus 7 into IA ln 1 by r dash minus of IA ln 1 by D. Now if you know that equation, right, logarithmic equation, what is the equation of ln A minus ln B? What is the equation of ln A minus ln B?
Log A by B, sir.
Right, log A by B. Now, so if you eliminate this minus term, you can write log A by B. Now here A is 1 by r dash, ln 1 by r dash divided by, here B is 1 by D, 1 by D. So finally what you will get? Ln D by r dash. So the inductance of a conductor A is LA is equals to 2 into 10 power minus 7 ln D by r dash. So that's what we are obtaining from the only one conductor from 3 phase. Similarly, you can calculate LB as well as LC. Let me see how it will be after calculating that all parameters. Are you clear about how the pi A will be is there? Right. So this is the LA value. So after simplification of this equation, finally the inductance of a conductor A is given by pi A by Ia is equals to 2 into 10 power minus 7 ln D by R dash. Here numerator D is called as GMD, that is mutual GMD, and R dash is called as self GMD. If you just keep remember that if you want to solve any problem from the first unit, you should aware about how to calculate that GMD and GMR. Then only you can solve that any question and any problem. So if you're not doing this GMD GMR, you can't able to find that inductance value. So why? Because the entire problem is completely depends on that what is the GMD value among the conductors and what is the GMR value among the conductors. If you calculate this one, you can easily calculate the inductance of a particular conductor, right? So that is the importance of GMD and GMR. Now see, after finding this LA, similarly because of symmetry, conductor B and C will have the same conductance. So for LB also you will get 2 into 10 power minus 7 ln D by R dash. Why? Because all are symmetry, so all are placed in the same distance, right? That is the reason we are getting that all inductance of conductor A and B, C will get same. So the equation to gives inductance per phase of the three phase, right? So we have R, Y, B, right? So I am considering A, B, C. So just LA is given by that one phase. So we have for a similar phase 3, 1, 2, 3. So if you are adding this 3, then you will get that total inductance of a three phase. But the equation 2 gives only inductance per phase. So only for one phase it will give that. So that is R. So we have to calculate Y and B. After that we have to add 3. So in that adding the 3, we don't want to just we can't able to just add like this. Why? Because these are connected in parallel. So how we can calculate here? By calculating that average value LA plus LB plus LC by 3. After that only you can calculate it. Why? Because these conductors are connected in parallel. So this is the inductance of a three-phase line with equilateral and symmetrical spacing. See, all derivations are very simple. When the simple means if you understand the concept, it means that how we can calculate the flux linkage of a particular conductor, how we can calculate GMD, how we can calculate GMR, what is the equation. So initially we derived two equations, right? One is inductance due to the internal flux and inductance due to the external flux. If you remember these two derivations, then you can easily solve any derivation from the inductance value. So the basic thing is you have to remember that what is the value of inductance due to the internal flux, at the same time what is the value of inductance due to the external flux. If you remember these two formulas, then you can derive that any derivation, any circuit about the inductance value. So just to recall that derivation, final derivations daily. So then only you can remember the formulas. Now we go for second topic, that is inductance of a three-phase line with unsymmetrical spacing. So unsymmetrical spacing means the distance among the conductors is not equal. So I simply say that it is unbalanced condition, right? So this is the structure of conductors when we are taking in inequality. It means that the distance among the conductors is not equal. Same thing here also. I am considering that three conductors A, B, C having the radius R, and each conductors carrying that IA and IB and IC. So these 3 points are common for this any three phases. So we have considered three conductors and how the placement are happening among the conductors and what are the current flowing through the each conductor. So that is the initial assumptions. So when the conductors are not placed in the equal, then it is called as unsymmetrical spacing. Just keep remember that. When the conductors are not placing in equal distance, then it is called as unsymmetrical spacing. If the conductors are placed in equal distance, that is called as symmetrical spacing. So the same question I will ask in strip test. So just remember that. Now same thing we are going to find that inductance of a conductor A with respect to the B and C. So let me see how it will be happen. Right. But here we can't able to use that equation IA plus IB plus IC. Why? What is the reason? In this case we can't able to use this equation. What is the reason?
It is unsymmetrical, sir.
right? So because of it is unbalanced, unbalanced condition, it means that the current carrying by the each conductor is different, so we can't able to use this equation. In this condition, in this situation, we go for another method. Let me see what is that method. Now what we obtained, same thing here also we can obtain, but we have to eliminate this IB and IC. So that is the main problem in this condition. Why? Because we can't able to use this equation. Then how we can eliminate this IB and IC means I will show you. So finally, from this equation, I'm taking common as IA value. Why? Because for calculating the IA, I need two terms. One is psi A and IA, right? That's why I'm taking the common IA. Then you will get ln 1 by r dash plus IB by IA. Why? Because I'm taking the IA, right? So you will get IB by IA ln 1 by DAB plus IC by IA ln 1 by DCA. So finally, the inductance you can write pi A by IA 2 into 10 power minus 7 ln 1 by r dash plus IB by IA ln 1 by DAB plus IC by IA ln 1 by DSA. Now we have to calculate that what is the value of this one, IB by IA and IC by IA. Now just see this, how the conductors are connected here. First here that if it A, B and C. So based on this position, we have to make the phasor differences, phasor distances. Okay, phase angle we have to find that based on the distance, based on the location. Now we have to find that what is the value of IB by IA, IC by IA. That is the main intention here. Now do you know that how we can calculate that? Right. So based on the phase angles. So this is the position of A, and it is the position of B, and it is the position of C. So we will take the three phase angles. It is called A, B and C. Each the phase angle between the each phases is 120 degrees. Right. Now what is the current with respect to the, so let's consider A is the reference vector. Now I can write IA bar, the current IA bar is equal to, with respect to the reference vector, IA into 0 angle degrees. So it means that the IA is flowing in the same phase with respect to the A phasor. So that's why we got 0 degrees. Now IB. So what is the phasor angle between that reference A to B? If you I already told you that if you want to take the phasor differences, you have to consider that anti-clockwise direction. So this is the direction you have to consider. Now what is the current, what is the current IB through the B conductor, that is IB, from with respect to the reference A. Let me see, from A to C it will take 120 degrees, and from after that it will take 120 degrees to this D. So totally we will get 240 degrees. So that's why the phasor angle of B with respect to the A, you will get 240 degrees. So here when all phases are 120 degrees, you can write IA equals to IB equals to IC, right? So instead of IB, I can substitute IA here. So this is only assumption. How do we can eliminate these two terms, right? Now next IC. So what is the phasor angle of current IC with respect to A? 120 degrees. So IC into 120 degrees, IC angle 120 degrees. Instead of IC, I can substitute IA. Now we found that all phasor angles. Now if we substitute these two terms, IB by IA. So what is the IB value? IA phase angle of 240 degrees divided by IA. So IA get cancelled. Then one angle of 240 degrees. You can write cos 240 plus J sin 240. This is the value by I by IA. So I by IA value is minus 1 by 2 minus J root 3 by 2. So that's why I said last two classes what is the how we can calculate that phasor angle. So due to this reason I told you that the last class itself, right? So this is the value we can substitute instead of IB by IA. Similarly IC by IA. So what is the value of IC by IA? So IA divided by IA angle 120 degrees divided by IA. So IA you get cancelled, then you will get one angle 120 degrees. That is, you can write cos 120 degrees plus J sin 120 degrees and final value here. Suppose if you take that in clockwise direction, you will get minus. So just remember that if you want to if you are considering in anti-clockwise direction, the angle phase angle should be, you have to consider positive. If you are taking that clockwise direction, you have to consider that minus, negative. So that is that you have to remember that while observing that, while performing the phasor diagram in anti-clockwise direction, we have to take that phase angle with positive values, and if we are considering in clockwise direction, we have to take that negative value. So after substitute these two values in equation 1, let we will see that what is the final value of LA. Right. See here, this is the equation after substituting these two values. Instead of IA by IB, sorry, IB by IA. So this is the term we got. We substitute IB by IA, and here IC by IA. See, after simplification of this all terms, you will get LA is equals to 2 into 10 power minus 7 ln 1 by r dash plus ln square root of dA by dCA plus j root 3 ln dAB by dCA. So this is with respect to the A. See here, just I will tell you that simplification here. So from this term, I'm separating that minus 1 by 2 term is separate and j root 3 by 2 separate. Similarly here, so finally we will get 4 terms, 1, 2, 1, 2. So 4 terms. So it is common same, and minus 1 by 2 this one. So after splitting this equation, we will get the 4 terms. Now here I'm taking that if you, this is then denominator, right? If you take this upwards, you will get plus here. Here 1 by DAB, right? So if you make this 1 by DAB to DAB, you will get positive sign. Same thing happen here. So here also you will get positive sign by bringing this upwards, positive sign bringing upwards, positive. So after this 1 by 2 will becomes square root. What that is 1 by root power 1 by root 2, 1 by 2. So here also ln DCA power 1 by 2. So here j root 3 DAB power 1 by 2. So like that. So why? Because we had to make that square root, right? So finally, well, in these two terms, the common thing is ln and square root. So ln and these two in plus. So when the two logarithmic function are addition, we have to multiplication. When the two logarithms are subtraction, we have to make division, right? So these are two are in addition, right? So ln square root of DAB and DCA. Similarly, plus j root 3 is common, and these two are in subtraction. That's why we got a division condition, DAB by DCA. Similarly, we can obtain for both LB and LC. So this is for LB. So how we can remember this means if you know this one equation, you can easily write. Why? Because we are finding that LB, that is inductance of B. So you will get two terms, BB and single AC. Similarly, in this equation also we are getting the two terms. Why? Because this is the term we decide that what is the inductance of particular conductor. So we are finding that inductance of a B, right? So we will get two terms, DBC and DAB, DAB and DBC. At the same time, for inductance C, how we can write for LA? LA is equals to 2 into 10 power minus 7 into ln 1 by r dash plus ln DAC into DBC plus j root 3 ln square root of DAC divided by DBC. So this is the equation we obtained for LC. So this is the difference between when the three-phase conductors are connected in symmetrical spacing. Symmetrical in the sense the three conductors are placed in the equal distance. Unsymmetrical in the sense the three conductors are placed in the unequal distance. That is called as unsymmetrical space. So this is about today's class derivation, right? So do you have any doubts here? Tushan Basha. What is the advantage? Three-phase double circuit. So why we are using that in three-phase transmission lines and double circuit? What is the reason? What is the advantage? Anybody? Why we are using that? Sure. I will send you. I will send you the PDF. See, I'm sending that same thing. What we so additionally I'm adding that to a class itself, right? So what we discuss till now, I will send you in a group. Okay, now, no problem. So what is the answer my question? What is the advantage of three-phase double circuit? Suresh, are you there? What is the advantage of three-phase double circuit? So no need to talk. You can just give the answer in chat box. Two not seven Riyaj, Kushan Basha, Rangana. Right, one answer is came. To receive more reliability. So in what way you can say that it is more reliability? So reliability in the sense, what is the meaning of reliability means without any interruption. So that is called as reliability. If we are using that three-phase double circuit means we can send the power in continuously. Why? Because the double circuit in the sense one circuit is for main purpose and the circuit is backup. So when we are using backup means if at the event of failure or maintenance purpose, so if you removing that one circuit, we can use the another circuit by transferring the power. So in this condition, there is not interruption will take place. So that's why three-phase double circuit has a more reliability, right? So this is about the inductance of a three-phase symmetrical and unsymmetrical spacing. In tomorrow class, we have discussed about how the transposition will be occur. So transposition will be what is the advantage of transposition and how we can calculate the inductance of a transposition conductors. So let me see in tomorrow class. So until what we discussed in today's class, I will send you that PDF. Just practice that all derivations. After completion of all derivations, we go for problems. Then only you can understand that, right? So do you have any doubts? I'm going to in this class. Right. Thank you.